Hello everyone, how's everybody doing? I hope you're doing just fine. Before we start, I got a couple issues. I want to remind everyone again, 7th Rational Physics Conference, Borås, Sweden, 8th of June. Okay, and here's the little information. Okay, and we're going to have our conference there. Some very interesting people will show up. If you plan to attend, make your reservations early. You can contact me through my Patreon site. Go to Rational Science, you'll find us there. Or you can contact me through Facebook. You can there's a Facebook site that you can look up with that title, 7th Rational Physics Conference. Okay, so you shouldn't have any problem locating it. It's free. Not sure what else to mention, but if you have any questions, just, give me a buzz. Okay. What else? Any questions that you have, any comments you want to make, please also raise them at the Patreon Rational Science site. Next Sunday, I'm going to be on JFG's program again, for those who are interested. And we're going to be discussing black holes. Black holes and dark matter. Very pertinent stuff these days, right? They took a picture of the first black hole. Okay, so we're going to be discussing black holes. Anyone who wants to join us, it's going to be at 1900 hours Quebec time, which is Eastern Standard Time, okay? So be there or be square. And okay, so let's get on with it. Just going to put a little summary of what I did the other day, which is the different ways in which the rope model explains the invisible phenomena of Mother Nature's. And here it is in one little picture. Okay, you have on the upper left, number 1 there, light. What is light? We say it's a torquing of a rope. Rope binds any 2 atoms in the universe. All atoms in the universe are interconnected. Number 2 there, it's the atom, and it's built with these same ropes. One thread goes to the center of the atom and builds what we call the proton. The other thread curves around and forms the electron shell. So essentially, an atom is a little urchin, sea urchin, encapsulated by a balloon. That's what an atom is. That's what we say it is. And it looks more or less like this, coming up here, more or less like that. You can see the ropes stop at the boundary of the atom. What continues are the electric threads, right? And they're going to build that little star in the center, which we know as the proton. What this shows, this model, is that an atom is not mostly empty space. Okay? That's the first thing that's different. The second thing is that we build it all with the electromagnetic threads. Electromagnetic, just to keep with convention, we can just call them threads, doesn't matter. Okay? All we're saying is that the entire universe is, all the matter in the universe is just a single thread, closed loop thread. And this thread tangles and turns into ropes and atoms and also neutrons. And there's a debate on that within the group, but that's what it is. Essentially, all atoms in the universe are interconnected by ropes because there is a single thread in the entire universe that makes up everything else. Okay? Bottom left, we have electricity, number 3 there. And what we have is a row of atoms. Really, it's a row of molecules that spin in situ. Okay, these are aligned molecules. They spin in situ, and by doing so, what happens, they release the threads. And the threads move around the row of atoms, which we will call a serpentine. So they just move around, the serpentine spins, swings the threads around, and those threads form these walls, which we call the magnetic field. And here, what you see here is just a cross section. You see just one line of threads. You have to imagine this as completely all around the row of atoms there, the row of molecules. Okay, so this thing is just sweeping completely around, and that forms the magnetic field that surrounds a wire. Okay. On the lower right, number 4, magnetism. The threads, you can see those blue lines there, violet lines and green lines. Those are the rows of atoms, really molecules, but we can, for simplicity's sake, I put them as atoms, okay, just so people can relate to the mechanism. And if you look at electricity, there, the green line of rows, that's what each one of those rows is. It's a row of molecules, essentially, and they're spinning. The ones on the top half of a magnet, not north-south, it's in the other direction. It's the up, the top section of a magnet and the bottom section of a magnet. And the top ones can spin, for example, clockwise and clockwise there on 2 magnets. When they both spin in the same direction, you can see that the threads latch on to those from the other magnet and pull on it. The closer they are, the more threads that are involved, and the faster the magnets are drawn to each other. When you turn one of the magnets around, they clash, they hit against each other, both on the bottom and on the top, and they push each other away. Those are the mechanisms. As you can see, we did all of this, we did it with the same model. We took 2 threads, we turned first the torsion of a rope, we bound them around, we twined them around. The torsion is the light. The atom is built from these same threads. The electricity is just the sweeping of, well, not the sweeping, but electricity is the rotation of a row of molecules. But by doing so, it also creates the magnetic field, which is just a bunch of gazillions of threads that are sweeping around the atoms. And we produce magnetism with those same threads by simply having them either latch on when you pull or hit against each other when they push. That's essentially the model. And we did it all with just this model with the rope and the threads. Okay, one piece is missing, and that's gravity. And gravity looks like this under the rope model. And what do we have here? Well, on the upper left, we have all interconnected atoms. All atoms in the universe are interconnected. The bottom left shows how 2 atoms are interconnected. You can see 2 atoms there, connected by a single rope. And those are hydrogen atoms, by the way. When the atoms expand and contract, they torque the rope. And that's the signal that arrives at another atom, and that's what we will call light. Upper right, we have the acceleration of gravity. When atoms are aligned on the same axis, essentially what you have is, in this case, one atom, number 1 and number 6, are pulling on each other. 2, 3, 4, and 5 are as if they do not exist because they're on the same axis. When the object, in this case the cylinder, moves closer to the cube, you can see that the ropes go out of alignment. They're no longer on the same axis. The closer they are, the more that the ropes fan out, and each one pulls independently, and that creates the acceleration of gravity. Another vision of this you'll see on the lower right. You see when 2 objects are far away from each other, they're all connected. All the ropes form like a single coaxial. When the 2 objects approach each other, the ropes fan out, and when they're very close to each other, the ropes fan out even more. In other words, each rope is pulling independently, whereas in the first case, where the objects are very far apart, they pull like a single coaxial. So as you can see, we can do this not only for light, electricity, gravity, the atom. We can also do it for gravity. We can also use this model for gravity. Why doesn't the moon fly away? Well, there you see why it can't. Because all atoms in the moon are connected to all atoms on Earth. Okay? The sun twirls the Earth around, like you see there. Let me see if I can make that a little bigger, even though I think, let's see, how's that? Okay, essentially the first scenario, the one on the left, is what we see. We don't see anything between the Earth and the sun, or between the Earth and the moon, or between any of the celestial objects. And now if we had God's eyes and we can see everything, well, what we would see, that's what we're saying that the model shows, or how the model explains this, is that what we would see is that all atoms are interconnected and the sun is simply twirling the Earth around like, I don't know, Lilliputians would spin Gulliver around by gazillions of ropes. Okay, they would just twirl them around the air, and that's what's happening here. And that's the reason the Earth doesn't fly out of the solar system, because essentially it's physically bound to the sun. Okay, you might say, well, is that true? Here it is. I showed it last week. I'll show it one more time. Here's Mr. Richard Muller. He's a professor at Berkeley, and he says that, so for example, if you have the Earth, there's a big mass here, and you have you with your little mass here. Every atom on Earth is pulling on every atom of you. You're also pulling on it. The amazing thing about gravity is that it goes right through things. What's that a description of? Well, that seems like a description of what I just described. It's a description of two objects bound. Every atom of each of the two objects is bound to every atom of the other object. Okay? That's the model. That's the model. As you can see, it's kindergarten stuff. Once you get to know it, it's a no-brainer. And you say, well, Bill, can the universe be so simple? How do you know that it's true? Well, the first thing, we don't know if anything is true. True means that you believe in something. You want to believe that your wife ran away with or slept with your neighbor. Well, it's truth to you, right? Maybe it did happen, maybe it didn't, but if you believe it, it's true to you. So there is no such thing as truth in science. Truth just means that you believe in something. Okay? There is no proof, there is no truth. Okay? The other thing is that not only we don't prove anything, but what we're doing here is explaining a mechanism. Okay? What we're doing here is explaining a mechanism. And, all we have to do is understand the mechanism. You don't have to believe in it. You can have a separate mechanism for all we care, or all we know, right? You might have a different way of looking at this, and that's fine. Everybody's got his own religion. All I'm saying is here, I'm showing you a mechanism that explains gravity here, electricity here, magnetism here, light here, the atom here. Essentially all the invisible phenomena that we have out that Mother Nature runs. She's the puppeteer. She pulls all these strings out there. We don't see the strings, but we see the puppet moving. And the question is, if Mother Nature does it with magic, does action at a distance, especially with magic, or she does it but with mediators, physical mediators that we can't see. Okay, that's what you need to look at here. That's what this site is about. This site says, look, Mother Nature doesn't use magic. If this object here, let's see, I can do it with 2 balls. If this ball object, right? Can affect this ball from a distance. This one shakes up and down. You can see that this one shakes up and down when this one shakes up and down, for example. Or there's some pulls and that one goes in the same direction. And you can see that there's somehow tangled, entanglement, as they call it, gravity. You know, this one swings that one around. You have all these action at a distances, okay, phenomena out there. Does Mother Nature use spirits between the two objects? What does she use between them? Is there a physical mediator? That's the question. And in this site we say, yes, there better be a physical mediator, for otherwise you're doing religion. You're introducing magic in that same space. You're saying she's doing this with spirits. You know, the horse somehow pulls on the farmer pulls on the donkey or on the horse, and he doesn't use a rope. He does it with magic. He just pulls, and the donkey comes towards him, and there's no rope. There's nothing there. He's just going like this, and somehow the donkey comes nearer and nearer and nearer. And you say, how did he do that? Does he use magic? Is that what it is? This is what you have to think. Whether we can do physics with magic, or we're going to put a physical object in there. Okay? And the way we do it in physics, in real science, is you make an assumption. You make an assumption. You say, let us assume. Let us assume. Let us suppose that Mother Nature has this or that. Maybe she has particles. Okay. Let's simulate a phenomenon with particles. Let's see if we can simulate it and make sense of it. So, here's the, the farmer. He's pulling on a donkey. Does he throw rocks? Is that how he's pulling donkey? By throwing rocks at the donkey, and that's somehow providing negative motion, and the donkey comes near him? Is that how Mother Nature does things? Does that make sense? Does she send waves? The other day they discovered gravity waves. They proved that they got a Nobel for it. So is that how Mother Nature runs her cosmic universe, her cosmic ocean? Does she throw waves? Waves of what? We can say, well, that's irrelevant. Okay, fine. Secondary issue. But how do you explain the mechanism? How do you throw waves? The Earth throwing waves at the moon and pulling it in. Can you explain it with waves? Can you explain it with any one-way mechanism, whether particles or waves? This is the issue. Can you simulate the mechanism with waves or with particles? That's the issue. And I'm saying you can't, not rationally. You can do hocus pocus and say, well, we have energy and we have mass and we have force. You can have all these concepts, mathematical concepts, equations, numbers, units. And you can say, well, I can explain it with energy. I can explain it with mass and gravity. And see, the acceleration of gravity is so much. And, you can do all that hocus pocus. None of that is a mechanism. I want to see a mechanism. To see a mechanism, you have to make an assumption of the invisible entity that serves as a mediator first. Second, if you can do that, well, make the movie. Show me the movie on the screen. I want to see the mechanism on the screen. Yeah, let me show you a mechanism. Okay, here's a mechanism for you. Here's how a car works. Okay? Here you see the engine, and it shows you all the parts. What are they showing you? Physical objects. All of them are physical objects that you see in there. And they're going to label them. They're going to label all these parts, okay? And then they're going to show you how, not only how it runs, but you can see that the pistons are pushed downwards here. You can see the gas coming in, and there's an explosion, pushes the piston downwards, okay? So you can understand the mechanism. Okay, of course this is a synthesis, right? But what I'm saying is, all you see is objects and mechanisms here. It's all mechanical. Now this is quite complicated, okay? You can see there's a lot of parts here, a lot of names for each part. There's motion. You know, this is a pretty complicated thing that you're seeing here, okay? Not everybody can relate to this. I mean, you got to really sit down and think about all these parts and what they're doing, because it's not just A plus B. It's not 1 plus 1, okay? Now let me show you something much more simpler. Okay, now watch it, okay, because you might have to take algebra and calculus at the university level to understand this. Here you have it. Here's a magnet. This is a magnet. And it's just a piece of metal. It's not magnetized. Magnetism. Now, do you think this is much more complicated than what you just saw? Just now you saw all these parts of a car, motor, you know, the engine, and the gas coming in, explosion, you got the pistons, you got the spark plugs, lots of parts. Look at this. 2 pieces of metal. Do you think you need to go to the university to understand this? If God came and told you the secret, or Mother Nature came over and told you the secret of how this is done? Do you think you would, oh no, it's so incomprehensible. 2 pieces of metal, how can they attract each other? I think I have to go to another universe, maybe to heaven, to see how this is done. Do you really think so? Or do you think you just need to figure out what entity Mother Nature has between these 2 pieces of metal? Right here, right there, something there. You can see it pulling. You can, it's not see it, but you can feel it pulling already there. And the guy who tells me that it's push is an idiot. We have to treat him as an idiot. We have to respect him, treat him with the respect that he deserves. He is an idiot. Okay? This is pull. You can see it pulling. Nothing is pushing my hand. So you got to be a total loony to think that this is done with push, like so many people think out there, that it's push gravity and push magnetism. These are people who just want to insist on their particle and waves, one-way mechanism. Here you can see it pulling. So you got to come up with an explanation for this. And you don't have to take calculus to figure this out. Let me show you another example to see how difficult this thing is. Okay? Now please bear with me. I want you to see how difficult Mother Nature is, how complicated her universe is, how she runs her shop. It's so complicated, so beyond human imagination. We'll never figure it out, right? Well, let me show you. Here we have, this is what you see out there, right? Let's start slowly so that people get the idea. Okay, so you see this, maybe in the night. You don't see the farmer, what he's doing with the donkey. All you see is that somehow he's pulling the donkey in. He's affecting the donkey in some way, okay? And you say, how does he do that? Does he do it by magic? Does he throw spirits at it? Is he throwing waves at the donkey? Is he throwing particles at rocks? How is he pulling the donkey inwards? I don't see anything. It's invisible. Okay, so you get up close, a little closer, right? And now you see it. And I say, that was so easy. How stupid of me. Look how easy it was. He was pulling on a rope. He had it tied to the donkey. It was magic only until you couldn't see the rope. But once you made an assumption, or in this case you saw the rope with your own eyes, then it's kindergarten stuff. Did you have to take calculus to understand how the farmer pulled on the donkey? Do you really have to go out there and study a lot of algebra and trigonometry to figure this out? And let me show you another now. Here's this one. Let's see if you can figure out how this is done. Look at the mechanism, okay? It's going to be quick, so here it goes. Okay, how did Felix break the glass? And look at it a couple times, okay? Look closely. What the... is that... Does he do magic? Is he... he's just... doing some hocus pocus? Is that what he's moving his hand for? Look at it one more time. So, you don't see anything. You just see poor old cat here just waving his hand, and the window breaks. So how are you going to figure out how the window broke? Is this magic? Are you going to say, oh, we'll never figure it out? It's so complicated. I just cannot imagine. Maybe I have to take calculus at the university level to figure out how Felix, broke the window. What if we do something else? What if we make an assumption? Now you see what broke the window. Why? Because you see it with your own eyes. He took a horseshoe and just threw it the window. Now, did you need to take calculus to figure out how Felix broke the window? No, you just needed to make an assumption about the invisible entity if you did not see the entity. Of course, once we see the horseshoe, we say, oh, I know, that's kindergarten stuff. But see, it wasn't kindergarten stuff here when you didn't see the object. Here it was magic. Here you say, how did he do that? But once you see the horseshoe, then it's kid stuff. It's one of those things that see to believe. Do we need to see? Can't we just make a movie of what you propose and see if we can simulate the phenomenon with whatever mediator you propose? Isn't that the way we should do science? Isn't that the way we should do physics? Or do you think you really need to take a calculus course? You have these places on Earth. You have CERN, the Large Hadron Collider, right? SLAC, Stanford Linear Accelerator, Fermilab. You have all these places, and they tell you that they're smashing particles. They're accelerating particles and clashing them. Okay, so they're making the assumption that they're dealing with particles. Okay? It's an assumption. Now, they call it proof because they've been proving particles for the last 100 years since they invented quantum. They say, yeah, can't be any other explanation. It's particles all the way. So why don't they have pictures of these famous particles in their standard model? If you look at the standard model, you find the letter H for the Higgs. Is that what the Higgs looks like? Letter H? Does the electron look like a letter E? If they're for sure that these are particles, why don't they draw them? Why don't they illustrate them? You might say, well, what's the relevance of that? Well, I'll tell you what the relevance is. If I'm going to produce pull, action at a distance, this particle pulling on another, if the particle looks like a hook, I can say, well, I can at least imagine the mechanism. Because see, here you have a particle and it's got a hook. And the other one's a particle that's got a hook, and one's pulling on the other. So we can say, okay, if it's hook-shaped, then I can imagine pull at least. But if all particles look like balls, like golf balls, like bowling balls, whatever balls, then no, you cannot simulate attraction, not from one particle to another. And I don't care how many particles one particle throws at the other, you still can't produce pull. You cannot simulate pull. And so the mechanism is not there. We don't have a mechanism for attraction, especially for action at a distance stuff. We don't have mechanisms for pull. That's the issue. And so this site deals with something that you can visualize and you can explain, you can see the mechanism. You don't have to believe me. Of course you don't have to believe me. All you got to do is look at the mechanism, judge for yourself. Does that make sense? Can you imagine it? Can you make sense of it, right? You look at the mechanism of magnetism that I'm proposing. This guy's going like this guy's going in the same direction, they're both going like that. One is latching onto the other and it's pulling. You turn one around, now they're going like that, they're hitting each other and pushing each other away. Did I need to sell you anything? Am I trying to, deceive you? No, I'm showing you objectively a mechanism. And then that same mediator is what I use for gravity. I use that same mediator for electricity, for light, and for the atom. So it's straightforward. You don't have to believe me. You don't even have to listen to me. All you got to do is look at the picture and say, well, does this make sense? That's all you got to do. And if it makes sense to you, fine. If it doesn't make sense, well, you continue with particles and waves. If they make more sense to you, then you're in the wrong site, right? That's all I can say. Okay, so this site is, does physics, and we do it with objects. And one of the issues that you need to be aware of is that, people say, well, you're doing a lot of semantics, ontology, philosophy of physics or of science, all these words that they invented. They say, well, that's not physics. Well, we got to start somewhere with physics. And if you think that we've already got it covered, think again. I say that physics is done with objects. You need to have objects to do physics. If God comes tomorrow, or Mother Nature decides, wakes up with a headache tomorrow, and they decide to wipe out all matter from the universe, no gases, no atoms, nothing, light, everything's wiped out. You have nothing. Whatever nothing means to you. What is happening? What event is happening? What mechanism are you seeing? What are you visualizing? Of course, you wouldn't be there either, aside from that. But assuming you still had your mind, your eyes, you could see, what's happening? What's occurring in a universe where there's no matter, no nothing? The first rule, what I call the golden principle of physics, is you need an object to do physics, okay? And that's what we do here. So here's the golden principle. Physics requires an object. You can't do physics without an object. And so the next question you must answer, you're absolutely forced to answer, is what is an object for the purposes of physics? Are you saying that this is ontology? Are you saying that this is, you're doing philosophy, you're doing semantics? No, you need to establish the foundations of physics. And I'm establishing the foundations of physics. I'm saying physics requires an object. That's a non-negotiable principle. You can't even debate this. I'm not going to allow you to debate it, because you can't do physics without an object. Now, you can see the golden principle doesn't say physics requires math. Physics requires an equation. Physics requires an experiment. No such thing. Or a prediction. Physics requires an object. You absolutely need an object, because otherwise there is no physics. And if you don't put an object, you're doing physics with spirits. That's what you're doing. And if you put a concept, you're doing irrational physics. So the golden principle is non-negotiable. And then, of course, if you need an object to do physics, the next step is you need to define what an object is, and especially you need to distinguish it from what a concept is. So we say that an object is that which has shape. That's what an object is. What is a concept? Concept, a word that invokes or embodies two objects, or words that are treated as objects. Okay? So you need to define the word object before you define what a concept is. And concepts are not part of physics. In other words, not actors. We don't use actors that are concept. We don't use love. We don't say love moves mountains, not in physics. Maybe in poetry, maybe in philosophy, I don't know, and maybe in mathematical physics, not in physics. Physics, we use objects to do all the motions in the universe. So you need an object and you need to distinguish it from concepts. And the problem we have today is that mathematicians, the mathematical physicists, they do everything with concepts. They move concepts around. And when you say, look, you're using concepts, you're using semantics, you're doing philosophy. No. Doesn't work that way. We establish the foundations. That's why if you're going to say that defining words such as object, exist, location, motion, oh, that's ontology. Well, and you mean by ontology, you mean that it falls under philosophy. Then you're screwed up in your head. You're really screwed up. You need to establish the foundations of physics. Every book on the planet of physics should begin by telling you what an object is, what physics is about, what an object is. Obviously, you would have to say, physics requires an object. This is the definition of object. Then you can continue to talk about anything you want. But you should start that way. Not a single textbook of physics in the last 10,000 years begins by telling you what an object is. And yet, as you see, you can't do physics without an object. In fact, I got books here of physics, so-called physics, mathematical physics. They say force equals mass times acceleration. And they start with acceleration. They start with motion. Do they define the word motion? No, because not even Newton defined it in his Principia, in his Scholium. They don't define these words because they don't know what these words mean. And they don't care because they say, oh, that's semantics. You need to establish the foundations of the discipline. You need to establish the foundations. And the foundations are, you need an object. You need to establish what distance is between two objects. You need to know what location means. You need to know what motion means. And the number one word, you need to know what the word exist means. Physics is the science of existence. Physics only studies that which exists. Okay? And so that's what we do here. And I don't call it semantics, I don't call it ontology, I don't call it all those nonsense words or terms that the mathematicians invented. I call it physics. You need the foundations of physics. We don't have to know what a heart is, for example, like you would need to know for medicine. And we don't study law, you don't need to know what regulations are. No, for physics you need to establish what an object is. That's the foundation of the discipline. Not ontology, not philosophy, not, I'm going to do a little bit of Plato and Aristotle. No way. You need to establish the foundations of physics. Okay? So, what is physics? Physics requires an object, and an object is that which has shape. Once you establish that, a lot of the religions die instantaneously. Now you can't say God exists, God does not exist. Now you need to establish first what God is. Is God an object? Is God a concept? If he's an object, well, does he have location? Then maybe he exists. Otherwise, he doesn't exist. It's by definition. It's not because I believe. You just apply the definitions, we're done. That's the way it works in science and physics. It's objective. You work off of the definitions. Okay? Okay, so where did we leave off last week? Well, last time. We left off with Mr. Maxwell, okay? And he had these 4 equations he's famous for. Very quickly, very briefly. I covered this a little bit the other day, but here they are. Essentially, what you're seeing here is his 4 equations in physical form. This is what the equations imply. This is what the equations mean, okay? Number 1 at the top, where you see Mr. Lagrange, actually Joseph Lagrange from France. He was an Italian originally. And Carl Gauss, who essentially came up later. And in fact, Maxwell came out later and even improved on that. But essentially what they're saying is that charges, if we're going to talk about charges, whatever charges means to you, whatever charges are, flow from positive to negative. Okay? So again, you can see they're using the word charges. There's no physical object called charge. Charge is what my wife does with her credit card. That's charge. Okay, so whenever people say charge, they're referring to a value, to a number and a unit. That's what charge is. There is no standalone physical object called charge. But that's what these people were saying all the way to today. Today they still use the word charge to refer to this thing. So we haven't made any progress since the days of Lagrange. Okay, on the upper right, you see the second equation, Maxwell's second equation, and that's that you don't have a monopole. Magnets have two poles, and a lot of people don't like that. Even today, they try to prove at all costs that magnets can have a monopole, that they have been able to isolate a monopole. And again, there's no such word as monopole. Okay, no standalone object. If you're going to argue that there is a monopole out there, or that you've been able to isolate it or whatever, draw it. Get a crayon, get some watercolors, get chalk, and draw. I want to see what this monopole looks like. Otherwise, you're not doing physics. We need a physical object there. Okay? Now, you see over there, number 3 at the bottom, a changing magnetic field induces a current in a conducting coil. Okay, so if you introduce a magnet inside a live coil, it'll increase the electricity. And vice versa, if you have an electric current, it creates a magnetic field around it. Those are the 4 equations that Maxwell essentially, in other words, this is the physical explanation, or the physical description. Really, it's not an explanation. It's a physical description of what his equations represent. Okay? Okay. But Maxwell is known for another more important, if I can find it here, Maxwell is known for a different kind of, see if I can get it, there we go. Maxwell is known for discovering this equation. This is his most famous equation. Maxwell is saying that if you take the mu and epsilon, which stand for the magnetic permeability and the electric permittivity, okay, I'm going to get to that in a second. You take the 1 over the square root of that, that's the speed of light. And not to take away anything from Jimmy here, you know, I mean, he had to break his head to figure that out, okay? And so I really tip my hat off to him for coming up with it. This is not some mean, you know, some simple stuff. He really broke his brain on this one. Okay, so you got to hand it to him. And this comes at the heels of other attempts to try to figure out, you know, the speed of light. They did it empirically. And here you have the first one. Here's Mr. Galileo. And he has his assistant on another mountain. And what he does is he uncovers his lamp. And the other guy has to uncover it. As soon as he receives the signal, he's going to do it, you know, he's uncovering his. And this is the way they try to figure out the speed of light. Well, of course, they finally concluded that the speed of light is instantaneous because they couldn't, it was so fast that they just couldn't measure it. They couldn't time it, okay? And that was our first attempt. Then we have Romer, you know, Romer comes in there. And he calculates essentially with the orbit of Jupiter. He's got the moons of Jupiter coming behind Jupiter. And there's a delay in the moon Io, especially the first moon. And they saw that it came a little later. And that's because the Earth was farther away. And so Romer figured out that it was due to the speed of light. So he figured out that the speed of light was not instantaneous as Galileo and René Descartes believed. Okay. Okay, so was that the only attempt? No, then we had Mr. Bradley. He, I think it was he studied it from 1725 to 28. And he came up with what is known as parallax or aberration. Essentially, what you have is the motion of the Earth and light arriving at an angle as the Earth moves through the ether. And he calculated that angle, and he essentially calculated the speed of light. The The last guy that came up with something new was Mr. Fizeau, and he had a tooth wheel, and he shone light through the wheel. The light either hit the tooth or went through the hole, one of the two. And he had this wheel spinning in place. So as the wheel spun, light was able to hit and miss, hit and miss, hit and miss. He had the speed of the wheel. He had the distance to the mirror on the other side of the mountain. He was far away from the mountain. And through a mirror, he was able to see, detect what was happening. Well, he just made a calculation, and he figured out that the speed of light was close to 300,000 kilometers per second. So that's when Maxwell takes over, right? And when he does this calculation, and let me put that up there again, when he comes up with this equation here, he figured out that it was almost 300,000 kilometers per second. And that's when he said, oh, look, this is the same value that Fizeau had. Fizeau did it in 1849. Maxwell is he's 1872, 1873, some 20 years later. And so he looks at this and says, this is probably the speed of light that Fizeau measured. But he was able to calculate it instead. He didn't do any experiment. He just said, look, we've got permittivity, we have permeability, and we can come up with this equation and figure out the speed of light just by a calculation. And that, again, no mean feat. It's quite a bit of footwork there, some mental mathematical work. What is permittivity? Well, let's look at permittivity. Let's see what it is. Let's see what this thing means. If you take a capacitance meter and you take two plates, a red one and a black one in this case, and you put a little separator there, okay, and you measure the capacitance, it has a certain capacitance. If you put more chips or whatever, more separations, you have less and less capacitance. The greater the distance between the two plates, the lower the capacitance. And there on the lower left-hand side, you will see the curve. It's an inverse curve. In other words, the greater the distance, the lower the capacitance. And he made the calculation, they made the calculation, and they figured out what the capacitance of space is in this using this method. What is permeability? And again, just quickly going through these. Permeability, you have two magnets, and you put, for example, an iron bar, you can put copper, you can put different metals in there, and it'll increase the permeability. In other words, it'll increase the magnetic force. And so they said, well, what happens when you don't put anything? Well, in the case of air, it's very similar to vacuum, and that's the permeability of free space, as they call it. Okay, so these are the values. These are the values that were determined already in the 19th century. And what Maxwell does is he takes these values and he does this calculation and he figures out the speed of light. Okay, so we have the speed of light, but we have no idea what light is. What are those little lines that Mr. Maxwell had in mind that are moving there? Well, what are we looking at? We're staring at vectors. That's what those arrows are. They're not engine arrows, they're vectors. What is a vector? It's got magnitude and direction. The blue ones are facing upwards. Okay, those are arrows. Those are just values with a direction. And the other ones are facing sideways. So what is this thing? Well, what are we looking at? Is this a physical object? Can we say that, oh, we discovered the nature of light because we are able to see these vectors moving? Well, what if I were to put something else? What if I were to put, for example, here, how's this? Here's a wave of numbers. How do you like that? Is that a physical object? Can we say, oh, that's a wave of numbers? Is that a physical object for the purposes of physics? Can we use this and say, oh, light is a wave of numbers? Or how about this one? I got a better one. Here's the good one, you know. Here we have a wave of energy. How's that? Huh? So we have waves of numbers, waves of energy, and waves of vectors. Is that what light is? Is that the mediator of light? Is that the what Mother Nature uses to run her shop? So this is the problem. The problem is that all of these are concepts. And even though Maxwell's effort at discovering this relationship in terms of meters per second is valuable, yes, we know it's fast, but you know, light is fast. Is that good enough? Is that close enough? It's fast. What we need to do is figure out what light is. And here, you know, Maxwell says, well, it's an electromagnetic wave. It's a transverse wave. So what is a transverse wave? You know, what is a wave? A wave of what? And that's, you know, when they use the ether. They say, well, what we're staring at really, you know, the way this runs is the ether. The movement, the vibration of the ether. And we had this throughout the 19th century. Towards the end of the century, 1880s, we have Mr. Michelson and Morley, and they said, okay, we're going to try to measure the ether. There's a big debate on that, and again, I always run out of time to be able to really cover it the way I want to. But the point is that Michelson and Morley, as far as the majority of people out there, not everybody agrees, okay? But as far as they, as the majority, in fact, as far as I know, Michelson did not believe that he disproved the ether, okay? That's my conclusion. But most people say, oh, he proved that there is no ether, okay? Because light ran in fact, I think I've got the, let me show that somewhere in here. If I can find it. Do I have it? Oh, here it is. Well, one of them. Let's see if this one's the one. This is the experiment that they ran. Essentially, a couple mirrors. They ran light through the mirrors, and they showed that no matter which way the Earth was moving, the speed of light did not change. Okay, and here's a dynamic version of that same thing. Let's see if I can find it here. Got so many of these. Here it is. Give me a second here. There we go. Okay, this is the dynamic version of what they did. Essentially, they ran a light through a mirror, and they were able to show that there is no ether wind there. I put the wind so that you can see the wind. There was no wind, no ether wind, and they expected to see it in one direction, not in the other. Okay, they didn't, and so most people concluded that there is no ether. And yeah, you have people even today who vouch for the ether. In fact, the official version, by the way, is that there is an ether. And, you know, quantum mechanics holds that the famous empty space is really made of virtual particles, made of energy, made of virtual particles and fields, vibrating fields, what they call fields that are excited, exciting fields. So, you know, what is that? That's the description of the ether. And so, again, we get to the point where I started a couple weeks ago, where you say, well, what is this ether? Is there such a thing as an ether? Is it a bunch of little balls? Are they infinite? Is the ether the same thing as space, or is space something different than ether? Is space what encapsulates each little ball? In fact, I have a little picture here to illustrate that as well. See if I can find it. Here it is. Here are the ether balls. I need to know what the white stuff is if it's different. And it's got to be different because each little ball is contoured or encapsulated by that white stuff. So, you need to identify the white stuff if it's different than the balls, which in this case it is. If, on the other hand, there are no balls, it's just ether, whatever ether means to you, you need to identify what that is. What do you mean? Is the ether made of little balls? If it is, then each ball is contoured, and there's something other than the ball in there that's giving it contour. So you can't escape it, and you need to define what that white stuff is. That's the big problem of ether. That's the first big problem. The second one, is it infinite? Does it extend infinitely? If it does, it violates the definition of object. Object is that which has shape. There is no object that is infinite. And so we run into these contradictions, and these are the issues that people don't answer, and that, most people say, well, that's semantics, that's ontology, that's philosophy. No, it's physics. It's physics because it violates the foundations of physics, at least as we understand it here. And yeah, there is, people don't like it because, here we're saying, look, you need to resolve these issues. And people say, well, that's not physics. Physics is running an experiment, doing some math, calculations, measuring, making predictions. Not here. Here we do something else. We're saying, look, you're going to introduce your ether. I want a drawing. I want you pick up a crayon, draw it, and show and explain, because I guess you can't draw something that's infinite, but, stand for your proposal. Stand behind your proposal. Justify it. Show me that the ether is there, that it's infinite, that it's made of particles, if that's what you think it's made out of. If not, what is it made of? Draw it. Just draw it. Point to it. Say that's the ether. And if it's contoured, I need to know what's outside of it. That's how simple it is. And see, we don't have that problem with a rope, because with a rope, space is nothing. What we mean by nothing, that which doesn't have shape. We have something and we have nothing. Black and white, antonyms. So now it's very easy, straightforward, no questions asked. If it has shape, it's an object. If it doesn't have shape, it's nothing. This is something, this is nothing. Very simple, very straightforward. And then the something is a single thread that's floating out there. And that thread turns into atoms, ropes, some people debate, but neutrons as well. So that's the story for today, okay? And we'll continue with this line of thinking. Offend who it might offend. I'll continue with this line of thinking on Wednesday. We'll see you then. Bye-bye.